Today, we will build a custom subgraph to index both on-chain and off-chain data using file data sources and the graph. After completing this walkthrough video, you'll be able to build your own custom file data sources subgraph that you can use to power your dApp. To read a written version of this video tutorial and view a repo of the final version of this subgraph, check out the links in the description below. Now, why might we want to build a subgraph with file data sources that indexes both on-chain data and off-chain data? Storing large amounts of data on-chain is expensive. To get around this cost, developers store large files on off-chain protocols such as Arweave or IPFS, and then record the ID of that large file on-chain for reference. Once this data is stored off-chain and linked through an ID, we can access this data programmatically. The easiest way to source this data from multiple locations in a decentralized pipeline is to build a subgraph using file data sources and the graph. Currently, subgraphs can index over 40 chains for on-chain data and IPFS and Arweave for off-chain data. Check out the links in the description for any updates on on-chain or off-chain data sources. So, let's get started building. Here are the steps to building a file data sources subgraph. First, we confirm our data's architecture. There needs to be on-chain data indexed by the graph. There needs to be off-chain data on Arweave and or IPFS. And there needs to be an on-chain event that contains a valid off-chain file ID from Arweave or IPFS. Valid IDs are, for Arweave, a transaction ID or a bundler ID, and for IPFS, the CID or the CID with a file name. The second step is we need to scaffold our subgraph using the graph CLI. We'll target the smart contract that emits the event that contains the valid ID. The third step is to customize our subgraph. Our subgraph.yaml will include file data source templating. Our mappings file will include file data source triggering, file data source handling, and off-chain, on-chain data separation. And our schema.graphql will have off-chain and on-chain data separation as well. And finally, we'll deploy and publish our subgraph to decentralize our data pipeline. Let's walk through each step together. Let's confirm our data's architecture by starting at Lens Protocol's official website, and we'll go to the documentation. Here, we can see all of the deployed Lens Protocol smart contracts. We're going to take a look at this smart contract. This smart contract here is a proxy smart contract, and as we can see, it's deployed on Polygon, which the graph indexes. If you need to review proxy pattern smart contracts, check the link in the description. Proxy smart contracts emit their events, as well as their implementation smart contracts events. Let's dive into this proxy's implementation smart contract so we can see all possible events emitted by the proxy. In the implementation, we can see a post-created event that contains a URI that has an ID that we can use to look up files on Arweave and IPFS. We will extract this ID from the post-created event and trigger the appropriate file data sources indexing of the associated Arweave and or IPFS data. One final thing to note before spinning up our subgraph, these are the valid IDs that we're looking for anytime we want to trigger file data sources indexing. For Arweave, we just need a transaction ID, and for IPFS, we either need version 0 or a version 1 CID. That CID could just be a plain CID or a CID with a file name attached as seen in this example. With that covered, let's spin up our boilerplate subgraph. Let's spin up our subgraph super quick. We're going to go to Subgraph Studio, and then we'll create a subgraph. We'll name it Live Demo Subgraph. The indexed blockchain will be Polygon, also known as Matic. We'll create a subgraph. From there, if we haven't installed the graph CLI, we'll want to do that there. We have, so we can just go to the next step and we'll initialize our subgraph, copy paste that into terminal and run it. We will select Ethereum as it's EVM compatible, Polygon is EVM compatible, and select the defaults there, and then Polygon Matic, that's what we need. And then we'll get our contract address. We'll go to Lens and get the proxy. We'll bring that in. Okay. Now the start block, we'll need to gather that from Miniscan, miniscan.xyz. It is fantastic to support subgraph development. And there it is. Copy paste. contract name. Best practices is to name the contract name the same name as the contract. So we'll copy paste that in there instead of naming it contract. Index contract events as entities. Yes, we will do that. Okay, our subgraph scaffolding is complete, and here we can see the subgraphs main files created. Very nice. We'll start at subgraph.yaml to implement file data source templating. Let's get going. Here we are in subgraph.yaml, also known as the subgraph manifest. This reflects the high-level shape of our subgraph. First, let's remove the previous entities that we do not need, and we'll add the post-created entity, and this will be a log of all the data emitted from the post-created event. We will also add the post-created event handler that will trigger every single time the post-created event is emitted from the smart contract. Now, let's build the file data sources template that will be instantiated with a valid ID. As we have two different off-chain data storage locations, we will create two templates as seen here. Each template will have a different name, but will use the same handle post content handler and will populate the same post content entity. Please note that entities that contain off-chain data must be kept separate from entities that store on-chain data in subgraph.yaml and in schema.graphql. Next, let's edit our schema.graphql. We're going to remove the three entities that were scaffolded out by GraphCLI and add the two entities we named in our subgraph.yaml, the post-created entity and the post-content entity. The post-created entity will be a log of the post-created on-chain event. It will contain the URI from which we will gather the off-chain data's ID. The next entity will be the post-content entity. This entity will populate with the data's hashed ID and the off-chain data itself. With the entities matching the named entities in our subgraph.yaml, as well as properly having on-chain and off-chain data separation, we're ready to move on to a little edge case that we have to solve. To address this particular edge case efficiently, we're going to proceed quickly since the primary focus of this video is learning to index off-chain data rather than troubleshooting an issue. This edge case touches on two key areas, ABIs and the interaction within proxy pattern smart contracts. For a more thorough exploration of this edge case issue, check out the written version of this video tutorial. Let's get solving this edge case. Typically, when indexing events from a proxy, we are getting the events from the implementation as well as the proxy smart contract. However, for our subgraph to be able to read all of these events from both the implementation and the proxy, we need to copy and paste the ABI from the implementation smart contract into our subgraph, so our subgraph can see all of the events passing through the proxy smart contract. Unfortunately, ABIs provided by block explorers may not be 100% accurate. In this edge case, the ABI provided by the Polygon block explorer does not contain the post-created event. So we must modify our subgraph's ABI manually. But don't stress. An easy way to do this is to compile the smart contract that contains the post-created event using Remix or any other smart contract framework such as Hardhat or Foundry. Once compiled, we will have the ABI of the post-created event to copy-paste into our ABI as such. There's the post-created ABI that we've gathered from the events.sol smart contract that we compiled here in Remix. I'll copy and paste that into our subgraph so our subgraph can see that post-created event, and we can then move forward. Let's move on to our mappings, where we will trigger file data sources indexing. This file is called lens hub initializable, and it is in the src folder. This is also just known as the mappings file. It takes the name of the contract we entered into the CLI when we first spun up our subgraph. Let's take this file step by step so we understand exactly what's going on with our mappings. First, when we spin up our subgraph does a lot of work behind the scenes to allow us to connect to these blockchain events. This work allows us to directly import the event data into our mappings through this import of the generated file lens hub initializable. We'll import the post-created event data and add the suffix event to it, so it's the post-created event. This ensures we know anytime we see post-created event, we're looking at blockchain data. Next, we'll import the entities we created from our schema. This will allow us to pass data from this post-created event into these entities, which we'll do in just a minute. Finally, we'll bring in the bytes helper from the GraphTS library to help us process the data coming in from our post-created event, as well as the helpers needed to trigger file data sources indexing, namely the data source context, and data source template. We'll go into these more soon. While we won't be using this handler, let's hop into the pre-generated handle admin changed handler and learn about the general pattern of what subgraph handlers do. Then we'll build our own handler from the post-created event. Every handler will have these three things. Number one, it will import data, be it event data, or as we will soon see, off-chain data. Number two, it will create an entity and give it an ID. A common pattern we'll also see from time to time is a null check to see if an entity has already been created in the database. So be in the lookout for those. Number three, it will perform logic on the data and populate the entity's fields, then save the entity. This logic can be as simple as passing data from the event into the entity, which this handle admin change handler does, or as complex as we'd like, as some subgraphs handle a lot of their compute within their mappings. Now that we understand generally what each of these handlers do, let's get building. First, we're going to prepare to use data source context. Now, data source context allows us to pass bytes, strings, booleans, and more from handler to handler. Now, this is a powerful feature that allows us a high level of coordination between handlers. To prepare for this, we'll create a key that we'll use in a key value pair later on that we'll call post ID. We'll come back to this post ID key and how it relates to data source context in a little bit, but for now, we're going to create a handle post created handler to simply gather the all important content URI from the post created event, and then we'll save it to our post created entity. We'll first create a new entity of the post-created type and pass in a unique ID that is a concatenation between the profile ID and pub ID. This ID can be anything as long as it's unique, which is why concatenation can be quite helpful at making it unique. We'll ensure this ID will be converted into bytes by using the bytes helper. Converting this ID into bytes ensures faster indexing, which is super helpful. Next, we'll simply log each of the emitted events from the entity's fields as seen here, and then we'll save. The most important field here is the content URI, where we can get the ID for our file data sources indexing. Now, in this next section, we will be preparing to dive into the content URI and identifying the off-chain data's ID by the URI string that comes just before it. To gather the Arweave ID, we'll just look for this string and gather whatever's behind it, and the same thing for the IPFS ID. While this is just a simple bit of logic of how to gather the ID, the main takeaway here is that this is where we should know our smart contract and the data passing through it well enough so we can gather the ID. In this next line, we can see that if the Arweave and IPFS strings are not found, we will end this handler. And if the strings are found, we know we have an ID and we can start data source context. Now, as we see here, we're going to create a new data source context, and we're going to pass this context between handlers. We're going to use the setBytes method on this context to set a key value pair. The key will be the post ID key that we set up earlier in this tutorial, and the value will be the entity's ID. Now, this is just a demo of how we can pass around data between handlers. Being able to pass data between handlers is incredibly powerful as it allows us to create more coordination between our data as it's being transformed. Go ahead and give this a try next time you are spinning up file data sources. Now that we've set the context as that key value pair, let's trigger file data sources indexing. Here we can see if Arweave index exists. We know we can go gathering the file ID at the 12th index of the arweave.net string. Once again, this is strictly typed because we know exactly what's passing through the content URI. We'll save that file ID as hash so we don't confuse the file ID with the entity's ID that we set earlier with that key value pair. Once we have found the ID, we are ready to trigger file data sources. Now, how do we do that? We're going to call data source template. Now, that data source template will reach into our subgraph.yaml and trigger the creation of indexing based on those templates that we defined earlier in subgraph.yaml. We're going to create a new template with context, and we're going to look for the template that we have previously defined in subgraph.yaml called Arweave content. We're also going to pass in the hash of which we've extracted. That's going to point the template at this hash to get indexing that hash. Then also we're going to pass in the context of which we prepared earlier so we can have good communication within our subgraphs handlers. Pretty cool. We're also going to copy that exact same logic from Arweave also into our IPFS files. And from there, we have everything we need to trigger file data sources indexing. So we've triggered the templates to begin indexing either the Arweave or IPFS content. That is awesome. Now we're going to need to handle that data. And so what we're going to do is create a new handler called handle post content. We're going to pass in the content that's coming in from Arweave or IPFS. And from there, we're going to go ahead and use the data source helper. As we can see, if we go to the data source string param method, we can gather the hash that we passed in just above. If we want the context, we can use the data source context method and we'll gather that data. And finally, if we recall, we set a key value pair as the context. So all we need to do in that context to get the value is pass in the key. So we're passing in the post ID key. From there, we will get the value, which is the ID. We have all the things we need to handle the off-chain content. So similar to the previous handler, we're going to create a new entity. We're going to call it the post entity, and we're going to pass in that ID that we gathered from that key value pair earlier. We're also going to populate the entity's fields, the hash and content field, with the hash and the content from which we are gathering from on-chain. We're also going to save this entity. So now we have a post content entity that is able to store off-chain data, and our subgraph is able to fully implement file data sources. Let's keep going. We're back into Subgraph Studio where we will copy paste more instructions into our terminal. We've already authenticated this computer in the past, so I won't do that right now. We'll go enter our subgraph with this cd command. And then from there, we will graph codegen and graph build. Graph codegen is the type safety, and graph build compiles our subgraph. Now it's ready to deploy. Copy paste. Give it a version. Our file data sources subgraph has been deployed. There is an endpoint that we can use to send queries to. Let's go back to Subgraph Studio and see how our subgraph is doing by sending some test queries to it. Now, this live demo subgraph is being indexed on centralized infrastructure. Let's go ahead and see how that infrastructure is doing with this test query. There we go. Post created on-chain events being brought right to us here. And then the post contents also being brought right to us. Let's scroll down a little further. There we go. What will you build? What will you build? Bloom into the new era of social. Very cool. So we have our subgraph that's running on centralized infrastructure. Let's go ahead and publish this subgraph so we can decentralize our data pipeline. Before publishing a subgraph to the graph network, it's best practices to update the metadata of the subgraph to be more helpful to other builders, as this subgraph and its endpoint will exist in a public marketplace known as the Graph Explorer. As we can see here, our live demo subgraph's name and metadata have been updated. Let's go ahead and publish our subgraph to the graph network on Arbitrum and incentivize the decentralized indexers around the world with 1K GRT to get to work indexing our file data sources subgraph. Okay, our subgraph has been published to the graph network where indexers around the world are able to hop in and index our subgraph should they so choose. As we can see here, one indexer has already hopped in and has started to index our file data sources subgraph. Should we want more indexers to index our data and therefore have more decentralization, redundancy, and competition for quality over our data's pipeline, we can signal more GRT on our subgraph to increase marketplace incentivization. Let's run a test query, and here we can see our data coming in not from centralized infrastructure, but from the decentralized graph network. Okay, so we have built a file data sources subgraph together. Now go ahead and get out there, build some file data sources subgraphs on your own. Thank you so much for joining me on this journey. Take care.